So I'm Adam Furmanek, and I'm very happy you came here. And today we are going to continue our journey in async programming, in async world, in .NET, in C# specifically, and we'll talk about how to re-implement async programming with some different primitives under the hood. If you attended my previous talks, you probably know that async is implemented with some continuation passing style, with some state machine under the hood implemented with the or created by the compiler. And today what we are going to do is we are going to see if we can do something different or how this could be implemented differently. Couple words about me before we actually move on. So I have almost 10 years of experience in software development. I've done a lot of backend, front-end, full stack, all that stuff of work. Currently, I'm working at Amazon. Currently, I'm working at in Alexa, doing some voice generation. And I'm also an author of .NET Internals Cookbook. So if you are interested in some internals of .NET structured as a series of questions and answers, then feel free to take a look at this book. It may give you some useful knowledge. Feel free to take a look at my blog. Feel free to drop me a line or email, Twitter, whatever works for you. And yeah, with that in mind, let's see what we have for us today. So the agenda is pretty short for today. First, we'll see why async at all, and we'll see how it impacted other languages. Then we'll understand what the operating system thread is and what other things which we could use to implement async programming in C# or the async and await keywords. And ultimately, we'll see some actual source code. We'll see some actually different implementation, or one of the potential different implementations, something which is super similar to what the Java world is considering right now, the Project Loom thingy, because they also want to have async and await in their language, but they are not necessarily trying to implement it using the or with the way it is implemented currently in C#. So we will see what other ways we could go and where we would end with. So first thing is why async. So actually, asynchronous programming is important for multiple reasons. One of them is that we would like to actually do some I/O operations under the hood. We would like to do some operation in the background, not necessarily on the main or foreground thread which we are currently running on, and we would like to see the result at some point. We would like to get the result, not necessarily figure out how the result is calculated or what machinery is running under the hood to get the result. We are just not interested in all these fancy details. We just want to get some code, run it, get the output. So there are multiple paradigms, multiple patterns in .NET or in C# platform to support all these things. One of them is called Asynchronous Programming Model, the APM thingy. So you probably recognize this pattern. You do have begin something method, you do have end something method, which completes the operation or synchronously blocks you until you get the result, right? So that is the idea behind the APM. And there is yet another pattern called event-based asynchronous pattern, EAP, right? So the EAP pattern works that we do have some background worker. We add another lambda to do some work, and the background worker takes care of calculating these things or running these operations, and then we just get the result, right? So these were patterns which we could use before, which we could use like originally in C#, initially in C#. However, their drawbacks were that, hey, they did work. Unfortunately, these patterns did not put the code as a first-class object, as a first-class citizen, right? So the problem with them was that, hey, we cannot encapsulate something as we can with the task class. So with task-based asynchronous pattern with TAP, what we can do is we can actually encapsulate the code to be executed in some kind of an object. Actually, it's an instance of the class, so we can encapsulate it and we can carry it around between different places in our source code, right? So we can see that we do have task. We can use the continue with method. We can use other things to actually carry the operation with us and attach some continuations later on. So they are being executed in different manner depending on how we utilize them. And all these patterns are generally cool. They generally work. However, the issue with them is that, hey, they do require some machinery under the hood to actually wait for the result. And this is why we do have the asynchronous programming. The async programming is based on the idea that we would like to await something, but not necessarily block everything. We do not want to block the thread when we are waiting for some result, right? So this is the idea behind async and await. And before we get into all these nifty details, a couple like technical words about the async and await itself. So the first thing is we can await anything which is awaitable. It does not need to be a task. We also know there is a value task, which is also awaitable, but we can actually await anything which supports the method called getAwaiter, which returns some type which supports the properties like is completed, uncompleted, get result, etc., etc. And the async itself means nothing. It's not something supported by the .NET platform. It's just the instruction for the C# compiler to get the code and transform it. This is very similar to the for each actually when it comes to how it's implemented under the hood. And with that in mind, what we can do is we can actually implement this super simple application where we can actually await the integer here. So you can see that we can await a number just because we do have the extension method called getAwaiter, which extends the integer type and just returns something which is awaitable, like task delay. So now you can see that we can, in our C# code, we can await integer and it just works. Because this whole machinery is based on this idea that we get some fancy type, which is the awaitable type, we pass it around with the state machine implemented under the hood, and this is how we implement the continuations. If you are interested in all the details, I recommend you take a look at my other talk, which is called Internals of Async in .NET, which is available on YouTube and was also presented here on the Svitla Smart Talks, where I explain how these things are implemented. But actually, the whole point of asynchronous code is that it does not block the operating system level thread. This is crucial because what we want to do is we would like to use async with the IO operations, and we would like to do the things in the meantime, but without blocking the current thread we are running on. So we get the thread, we call some potentially IO operation or some operation which will get the result for us without necessarily calculating it. And then we do something else on this thread. We do not block the thread. We can do other things like process different HTTP requests or process different, I don't know, UI actions, etc., but do not block the thread. That's the idea. And we will see during this talk that instead of blocking the operating system level thread, we can actually block something else and still have the async and await operators, and potentially with some other advantages. So async in C# is implemented as a coroutine compiler level transformation. This means that we do have this async keyword which we put on the method, and then the C# compiler steps in and rewrites the method. So it transforms the thing into the coroutines. We will see later what that means, that something is a coroutine. So that's the first part. The second part is we do have service locator for promise orchestration, meaning that we do have the synchronization context, which is basically a global variable taking care of orchestrating all the promises of the continuations around. And finally, we have statically bound promise factories, meaning that we encode the promise type inside the method. So we encode that given method returns task of something or returns a value task of something. So this is how we statically encode the type. And while all these three things, they are great together and they provide this fantastic async and await experience, at the same time, they are pretty nasty because, hey, service locator could be considered as being an anti-pattern. The same goes for statically bounding promise factories. Like, why would we even need to specify that this thing return a task? Maybe we would like to return something else, but we cannot control the code and it is compiled just based on the static things which we provide. So with all these things in mind, we'll first see what other things there are in computer science which could aid this situation. And later we'll see the demos how this could be implemented differently. Couple of words about the history. Async in C# was actually one of the first ones, and it went live in version 5 in 2012, and then it influenced multiple other languages, just to name a few on this slide. Probably the JavaScript implementation is almost like the same as in C#. Similarly, the implementation in C++. So all these implementations in Haskell, Python, etc., they are based on the same idea. We do have this coroutine transformation, which is exactly how we do it in C#. However, Java with version 17, they are going to release a final version of their project Loom, which is already available with previews, where instead of using compiler transformation, we use a user mode threads to support the async and await. So we will see if we can do the same in C#, if we can use user mode threads to implement async and await operations instead of using the C# compiler transformation. So what does it mean? What is the user thread? Before we get to that, we'll need to understand what a native thread is, what an operating system level thread is, because we mentioned that, hey, we cannot block the operating system level thread. So there are actually the Windows thread, which is at the very low level. It supports a couple different things, like it can be of two types, like foreground and background. It supports some metadata, which is used by the operating system to schedule the threads and to handle them. It has a stack, which by default is allocated to have 1 megabyte of memory, and with those schedules threads, etc., instead of processes. The thing about the native thread is it also supports the thread local storage. So with each thread, each physical thread, we may have some variable which we refer to in the same way. However, its value depends on which thread we are currently executing on. On top of that native thread, on top of that Windows thread, there is a managed thread, a C# a .NET thread, which wraps and then encapsulates the Windows thread. And it adds a couple of interesting things, like for instance, it has name. So we can name the thread and have this name in like memory dumps, etc., which aids debugging. But it also has different ID. The thing is, .NET never guarantees you that given managed thread runs on the same operating system level thread over and over again. It may migrate between physical operating system level threads. However, with current implementation, it does not happen. It would be pretty cumbersome. That's because that would break the synchronization primitives, that would break the thread local storage and other things. However, in theory, nothing stops us from doing it this way. So the managed thread, which encapsulates the native thread, is actually something which provides us in C# or in .NET generally the ability to create threads and run them and execute them on our machine. However, these are operating system level threads. What happens is we also may come up with an idea, hey, instead of having this very heavy thread managed by the Windows platform, by the operating system, or it could be Linux, OS X, whatever else, why not implement a threading library in the user mode? Why not have the green thread, which would be scheduled by our library? So the advantages of that would be that we do not need to have the heavy kernel switch every single time we do the context switch or we change threads. That's first thing. Second, we control the threading down to a very single little detail. And third, if we do have these threads, we can actually implement things which are useful for us. For instance, we could use them to implement async and await. When it comes to the green threads, or virtual threads as they are often called, this is exactly the idea. We have the thread which is scheduled by a runtime library or CLR or JVM or whatever else, but not the operating system itself. They run in the user space entirely, so they consume less memory, and in theory, they could be faster. And the name green thread comes actually from the Sun Microsystems company, which designed Java, and that was the original threading library name for the name of the original threading library. So they dropped the green threads around like Java 1.1 and then turned to using operating system level threads. However, now they are actually reinventing this idea or exploring it again because they would like to use the virtual threads to support asynchronous programming. So the advantage is, well, depending on where we run these threads, they can be started much faster because we do not need to call the operating system every time to get a thread, right? They also can be faster in terms of execution proficient because they can outperform native threads when we do some user space synchronization. If we know what we are synchronizing on, instead of using OS primitives, mutexes, semaphores, etc., we can come up with our custom primitives. And this is, for instance, what is being done in Chrome Google browser, right? In Chrome browser, there are multiple user mode like synchronization primitives, which are simply faster and consume less memory. On the other hand, they are not as versatile as other primitives supported by the OS itself. When it comes to disadvantages, it is important to understand that, hey, a green level thread or the user level thread needs to run on a physical native operating system level thread. There may be multiple green threads running on one OS thread, but it is important to understand that the green thread cannot migrate between processors, right? Because a single operating system level thread executes on a single CPU only, and it may be scheduled later on, but this cannot be controlled by the green level thread, right? JVM nor CLR cannot execute or cannot control that. When it comes to the I/O operations, they typically perform slower. That is because, well, for I/O operation, we need to go to the operating system anyway and ask for some data because it's OS who controls the data, the I/O subsystem, and we cannot do that on the green level thread. So this is where we actually have some performance penalty. And also, when it comes to the operations which we execute, green level threads or user level threads, they always need to go with asynchronous I/O. Why is that? Because if they block, imagine that we have, let's say, 10 user mode threads running on a single operating system level thread. If any of these green threads call an I/O operation which blocks, then all the green level threads are effectively blocked because the whole native operating system level thread is being blocked. So we need to go with asynchronous operations always. Otherwise, we will just lose all the advantages. We will lose all the advantages of the user mode threads. So these are the green threads, but there are also other variations, right? Depending on the platform which we use. For instance, in Erlang, we have a concept called green processors. Even they are super similar to threads, they actually do not share the data memory directly, and they actually can share memory but cannot modify it. So that's a bit of a simplification here. But generally, Erlang calls them green processors instead of green threads. Similarly, Go calls them Go routines. Julia uses green threads for tasks, so they call it tasks. Python uses tasklets, etc., etc. So there are multiple different names, and there may be multiple different tiny details or tiny like those slight variations of the same concept of the green thread. However, the actual implementation may be different in each of these platforms, may give you some other possibilities or may actually break in different edge cases, right? But this is the general concept of the user mode thread. However, now we come to the idea of coroutines. Imagine a regular C#, .NET, Java, whatever language function. So you start calling this function, you enter the method, and you just exit at the very end or wherever you put your return keyword, right? So this is the method. You call it, it executes, and it leaves. So this is a regular subroutine which executes just once, let's say. However, with coroutine, what is we can suspend the coroutine and resume it anytime. So the idea here is we can start executing the method, and then the method stops in the middle, like somewhere in the middle, and then it is being resumed in the same place or in some different place, but it's considered being the part of the same execution. So this is the idea of coroutine. The coroutine needs to ask someone, for instance, the execution environment, CLR, JVM, or whatever, to be suspended. So that's why we say coroutines are cooperatively multitasked. So coroutine steps in and says, hey, I want to be suspended now. And this is how coroutine gets like stopped for a sec. And then when someone decides, okay, let's carry on with this coroutine, it is being resumed and executed later on. So these coroutines are typically a language level constructs, and they are also called, like this is obviously a different wording for different concepts. When we do have generators, they are called semi-coroutines, they are subroutines, etc., etc. So the idea is, to give you some notion or some understanding where it goes, is we in C# language, we do have the yield keyword. So you can see that we do have this regular method, and here at this point, whenever we call yield return, we return some value from this method, but we do not stop executing this method, right? We just return a value, and if we return the value with like count was 0, then the second time we continue executing this function, we do not start again from scratch, so from here, which would result in count being 0 again. No, instead we carry on from here, we do another loop iteration, and when we return yield return again, this time we return 1. So this is the idea. This is the idea of these generators or enumerators in C# as we call them. And this is the idea of coroutine. So we do have a method which we can stop at any time and return some value. And you can also see that it is being cooperatively multitasked because it's the coroutine who decides when to be suspended. The coroutine decides, hey, I want to yield return now with this keyword, and the coroutine decides when it gets suspended. So just to give you understanding how it works in like C# level, when we get this code, this get counter with one simple loop under the hood, the C# performs the coroutine compiler level transformation, the same thing as we have with async, as we will see in a sec. So when we compile this, you can actually see that get counter method here at the very top just returns some type and does not perform any calculations, any loops, etc. Instead, in this type, we do have a method which is called moveNext, and which implements things with switch and case and couple other things, and it is here where the whole calculation is actually being performed. So we do have this for loop translated into the while loop, and we just save the number which we would like to yield return from the method in some field on the type, and then we just return true, indicating, hey, there was some value returned. And the next time we call the method, we enter the switch again and we jump around. So this is the idea behind the yield keyword. And you can see that it can be implemented on the C# level directly with this transformation. And the same thing is actually happening with async. However, there are a couple issues with approaches like this. First, whenever we do have the method which is a coroutine, we introduce the so-called function coloring. Let's get back to the code we have here, and you can see now that this method must return an enumerator, must return some generator type. Just like with async keyword, we have tasks. The same way with generators here, we have the enumerator. So we need to have this type of a method, this type of which needs to be returned, and we call it function coloring. That is because we cannot use these methods the same way depending on which context we are in. We'll understand that with async in a sec. And if you are also, the things like this may not necessarily be used in constructors or void methods. And they may also change your exception handling mechanism, and they obviously increase the memory allocation because we need to allocate this specific type. If you would like to get some more understanding of the drawbacks of async and await, I highly invite you to take a look at my other talk, which is called Async Biggest C# Mistake, where I explain all these things and why function coloring is wrong, etc., etc. So let's now see how these things apply to async methods. So we start with a very simple method, which has a couple of await keywords inside it, and we just throw as exception at the very end. And when we take a look at the state machine generated from it, we can see that our async method, first, it does not have any async keyword anymore. Second, it just creates some builder type, which has a very fancy name. And lastly, it just returns the task from this method. And everything is actually happening later on with this moveNext method, the same way as with yield keyword. And here the moveNext method performs some try-catch action. So we see that the exception handling mechanisms is different. And second, we do have this switch case with all these things, with getting awaiters and all the fancy details under the hood, which I explain into greater detail in my other talk. So what we would like to take, the takeaway from this slide is basically that, hey, the async method is being compiled to some other C# constructs. And now I mentioned the function coloring. We can see the function coloring is actually here because we do return the task type, or we can return task of t, value task of t, doesn't matter which one exactly, but we cannot just return anything we wish. We need to return something conforming to the specific protocol. And the problem with that task is, as you probably know in C#, if you want to call a method which is marked as async, you need to use the await keyword. You cannot block on the method synchronously. And in order to use the await keyword, the method with await keyword needs to be async. So we need to propagate async all the way up. And this is the function coloring, and this is the spread of this color across your code base, which is a pretty terrible idea when it comes to integrating some legacy code or non-async enabled code with the async enabled code. So the whole idea of how these things are implemented is called continuation passing style, CPS. The CPS is basically a form in which we, instead of calling the method and letting it finish and return the value for us, we call the method and we give it the continuation. We give it the lambda, which indicates which code needs to be called after the method is being executed. One of the forms of continuation passing style is the coroutine transformation. The other form is something we see here. Let's take the Fibonacci function. So the regular Fibonacci function just accepts one number, hey, which Fibonacci we would like to get, and just returns an integer, right? And then if it's 0, we return 0. For 1, we return 1. Otherwise, we just sum the Fibonacci n minus 1 plus Fibonacci n minus 2, right? So no magic here. And the idea is that when we call this method in this place, what we do is we let the Fibonacci method start and finish and give us the value back. So we wait for this method to finish, and then we control what we do next. With CPS, with continuation passing style, it's a little different. First, we accept the same parameter as before, but this time we also provide a continuation, meaning that, hey, Fibonacci, when you are done calculating your number, please continue with this continuation. So you can see that in case of when the n is 0, so when n is 0, previously we were returning the value 0, right? That was all. However, this time what we are doing is we call the continuation with value 0. Same goes here. For 1, we call continuation with value 1. And what happens now? For Fibonacci, first we call the Fibonacci with n minus 1, but instead of calling Fibonacci with n minus 2, because, hey, Fibonacci never finishes effectively, we provided the continuation that, hey, get the result you just calculated, and then please execute the rest of this code. And the rest of this code is call the Fibonacci again, and the Fibonacci again, we need to provide another lambda saying that, hey, get the result you just calculated, and then please call the original continuation we got here. Okay, so this is how the continuation passing style works. And previously, we were just calling Fibonacci, getting its result, and passing it to the console write line or to string formatting, right? This time, we call the Fibonacci, and then we ask it, hey, when you are done, get it as a result and pass it to the code which we have here. So to the console write line with the value. So this is the continuation passing style, which slightly restructures the programming, the way we program, the way we code our applications, because you can see now that effectively function never finishes. That's first thing. Second, we cannot use this, for instance, in constructors or in other places where not necessarily we allow to exit or to do some work before the function finishes. For instance, before the object is constructed, we should not be using the polyformic invocation. So effectively here we have the same. When we construct the object, we should not be calling some other code which may in turn call polymorphic invocation, because the polymorphic functions may not be ready yet. And there is yet another generalization of continuation passing style, which is called call with current continuation, and in short, it's called call CC. So this is a little tricky, and we cannot do this in C# at all. We can do it in different languages. And the idea is, instead of taking or passing the continuation explicitly, we get the original code as it is and transform it into the continuation and then pass it on. So let's take the C# code here. Imagine that we have a method foo, and the method foo just accepts like one method, this bar method, right? Which is action of integer. And we call this bar, and then normally we return free. So without using any call CC, what we do without any call current continuation, we just call method foo and we pass any lambda. We just pass the empty lambda here, right? This doesn't matter what happens. But the important thing is this lambda is being executed at some point, it returns value, but we return this number 3. And this number 3 is being then put in this place, in this console write line, so we effectively print the number 3. However, with call CC, imagine if it was in the language, what would happen is we just call CC foo here. So what happens is the continuation of this foo method, and the continuation is basically this code around, right? So this console write line, this is the continuation, is being transformed and passed as the parameter to the foo method. So it's passed as this bar. So now, because we do have this continuation here, when we call the bar, what happens now is we are actually calling this line of code. We are calling the continuation console write line, and because we pass the parameter 2 in this time it prints the value 2 to the screen instead of value 3. Why is this call CC useful at all? First, it allows us to implement different like programming instructions, for instance, looping, for instance, return from a function, etc., just by using this call CC. So in like a functional world, the call CC is like a go-to in imperative world. Go-to in C# or go-to in C++ allows you to implement everything, right? Functions, loops, for loop, while loop, function calls, exiting from the function. This all can be implemented with goto. The same in functional programming, call CC allows us to implement other structures or other things which are typically supported by keywords like return, etc. So this is the idea. And this concludes the coroutine part. But now we come to yet another thingy, which is like a mix of user level threads, which are being executed and scheduled on the user level mode, and the coroutines, which are cooperatively multitasked. And now we come to the world of fibers. Fibers are like user mode threads, which do support the cooperative multitasking. So they need to manually and explicitly yield the control. Just like in C# in the yield, we do call yield return. The same fiber needs to explicitly call, hey, I want to yield control, and you can get another fiber and execute it. On the other hand, fibers are system level construct typically. They can be like consider being a coroutine which are implemented by the operating system level or by the platform under the hood. So they do not need to be created by the compiler. You do not need to translate your code into this switch statement, into this, passing CPS, passing lambdas, but they are just implemented by the operating system for you, and you can just call it. And not surprisingly, they are supported by Win API, so by Windows, okay? And we'll see that they do have plenty of drawbacks. First, they may have a significant memory footprint because, well, they are just threads, right? And because they are not regular threads, there are some tricks how to actually beat down the memory allocation, right? For instance, you can see how these things were implemented in Rust or in Go, where segmented stacks were considered, etc. But generally, they do have memory. They do not let you to cut down on the memory usage. So you have the same memory usage as you have with the regular operating system level threads. On the other hand, the TLS, thread local storage, cannot be used with user mode threads, right? Because when you have one operating system level thread and multiple user level threads running on this single operating system level thread, all these user mode threads, they do have access to the same TLS, to the same thread local storage. So it may break your synchronization primitives, it may break your mutexes, just like with green threads, and just like with coroutines, if you execute multiple coroutines on the same level. Also, if you block on synchronous IO, you block all fibers. So this is the same as we consider with green level threads. So there are multiple drawbacks, and that's why fibers at some point were considered like not useful anymore. They were considered being harmful because you cannot control all the things, and because they seem to be very hidden inside the implementation. Then programmers may be surprised that TLS doesn't work, just to name a single thing here, right? On the other hand, you do have the same drawbacks with async and await. I again refer to my other talk, Async Biggest C# Mistake, which shows you that, hey, you cannot use TLS with async anymore because you can migrate between threads. You cannot use operating system level mutexes, right? Because you do not know on which thread you are executing on. So with the async programming being popular now, we actually see that, hey, we do have all the drawbacks of async programming, or all the drawbacks of fibers, without the advantages of fibers. So that's why Java wanted to approach and wants to approach the problem differently. And instead of re-implementing coroutine transformations every single time, they want to implement a user mode level threads which do not pollute your source code with function coloring. So when it comes to using fibers, there are a couple of things we need to keep in mind. First thing is we need to convert current thread into a fiber with the WinAPI method convert thread fiber. Then we can use basically the most important method is called switch to fiber, which allows us to do this cooperative scheduling. So the fiber says, hey, I want to stop now. Please do call some other fiber to do the work. And this is the idea how we are going to implement the async on top of fibers to get the advantage of user mode thread without pollution, without polluting the source code with the magical async and await keywords around. So let's now move on to demos. So let's see the Visual Studio thingy. So first thing we would like to do is we would like to start the application, see if it's working, and then analyze what it's doing. Okay, so we do have a regular async code. Okay, so what we do, and this is the scheme we will be using in all the demos. Sorry, let's make it a little bigger so it's easier to read.
Can you zoom it? Yeah, a little bit. That's perfect. Yeah, thank you.
Cool. Okay. What we are doing is we will have exactly the same scheme in all the demos, right? So what we want to do is we would like to run two jobs and run them in the asynchronous manner, meaning we do not block the operating system level thread. So we have two jobs. First of them is called run internal. What it does is we just print plenty of things, but we also call a nested function, and then we await this nested function. And in this nested function, the most important part is we call task.delay with 2 seconds, and then we await it, okay? So once we await this thingy here, if you understand how async works in C#, we exit this function, and we then return the future, the promise here. So we return the task. And then when we await the task here, we actually get back here, and we are allowed to call the side job method. So we are allowed to call another like task to be executed. The side job does nothing. It just prints something to the screen, okay? So you can see that the most important thing about this whole async and await is that, hey, we are executing our first task. So these are lines from the first tasks. But then when we await for 2 seconds, we interleave the side job somewhere in the middle. So this is the important part. And after we are done sleeping for 2 seconds, as you can see here, we carry on with the first task which was being executed. So this is the important part, and this is the clue of the asynchronous programming that, hey, we do not block the thread, we can execute the side job here. Okay, so this is the advantage. The problem of this is we need to use this task thingy, and whenever we call await, whenever we use the await keyword, we need to mark this method as async. So it needs to pollute the code base to the very top, which is a terrible idea because we would like to sometimes run this method from a synchronous context, and we cannot transform all the code around to be async enabled, and this is what async and await require from us. Okay, so what we are going to do now is we are going to re-implement async with the regular coroutines, so with yield return keyword, so you get some more idea how these things are actually implemented under the hood, okay? So what we will do now is we will comment out this, and we will implement async with generator. Hopefully Visual Studio does not crash, because sometimes it tends to when we are doing demos. And in the meantime, we can see how it is being implemented, okay? So there is a lot of bookkeeping code which we'll use, and please keep in mind this code is just for like purposes to show you the idea. It's not like race condition free. It may actually have some deadlocks on the middle. That doesn't matter, right? It may not propagate errors properly, etc., etc. This is not what is important for us. What is important for us is that, hey, this thing is, sorry, this is still the regular async thing, which I don't like. Is it being compiled? Let's rebuild it just to make sure. Async loom, yeah, okay. Let's rebuild it. Project not selected for build, 2 up to date, 1 skipped. Let me just tweak the configuration because probably Visual Studio missed something, and then we will get async loom pli and async loom. Yeah, so this should be hopefully okay. Let's try rebuilding it and let's see if it's working now. Okay, in the meantime, when it's being executed or when it's being compiled, let's see what's going on. So we do have basically collections to handle the tasks, and the idea behind the async thingy and how it works under the hood is on top of each thread, we basically have a message queue, and the message queue gets some message or gets some task, gets some lambda, and executes them one by one. And there is a queue. Whenever we want to continue with some continuation, the continuation is being put into the queue, and then the thread actually needs to go to the queue and rerun and run the continuation, okay? So we do have couple of collections here to indicate which jobs are ready to be executed now, which jobs we have like in the queue, and then we have couple semaphores, etc. The idea is we will enrich our enumerator, the regular enumerator returning integer, with the flag indicating, hey, what was the state of previous enumerator? Because we'll build a stack of enumerators. That's the idea. So whenever we call an enumerator, what we do is we basically get the underlying enumerator and ask it, hey, continue execution. And then if it was executed, if it returns some value, then we just return it. Otherwise, if we do not have a value from the current enumerator which was executed, then we remove it from the stack of enumerators and continue with executing the enumerator which is under the hood. So we get the previous enumerator and store it as a current enumerator and then carry on, okay? And we also have this method to push an enumerator on the stack. So what we do next is we create an enumerator for the run internal thingy, so the first task we would like to execute, and then we have the enumerator for the side job, okay? We do some bookkeeping, we initialize semaphores, etc., which is not super important for us, which does the job to get these things around. And now we get to this place where I mentioned that the thread needs to go to the queue and execute thing which is there. So we spin indefinitely, so we do while true. We get the things which are ready to be executed from the queue, and while we do have some jobs to be executed, we get the current job and we call it. We start executing it. Okay, and if it finished, we remove it from the collection. So we indicate that, hey, this thing was removed, and then we remove it from all the jobs. And once all jobs are done, once the queue is completely empty, then we just break. Okay, so this is the idea. Now, how do we implement our async and await? We implement async and await in the same manner as it was before. Instead using tasks, we use IEnumerable, and instead of using await, we just use yield return. So run internal basically returns IEnumerable of integer, and then we call the run internal nested, okay? And in run internal nested, we get the task and we wrap it into our magical thingy. And when we want to do await, what we do is we call yield return instead. Now, what does magic wait do? Basically, this method just gets the current enumerator and pushes it on the stack. And also because we are using tasks, we do not need to use tasks here at all. We could use threads, whatever else, but tasks are just convenient. What we do is we indicate that, hey, this thing is not yet ready. This task has not finished yet. So we just remove it from the queue. And then once it's done, like we could synchronize here with semaphores or whatever else, once it's done, we re-add it to the queue and indicate on the semaphore that this thing is ready to be executed, right? So this is how we wrap the task into the logic. And for IEnumerator, we basically just call the start method on it. So we wrap it into the stack, okay? So this is the idea how we build these things. So to sum up, we do have a plenty of bookkeeping code which holds the queue of continuations which we would like to execute, okay? We do have the enumerator with flag, which allows us to stack the continuations so they can be used one by one. And then we basically call the regular move next method of enumerator. What happens here in run internal is we start with one enumerator, so there is exactly one element on the stack. And once we get the run internal nested method, we basically put it on the stack again. So then when we do yield return, we call things like properly one by one taking from the stack. And you can see that, hey, this thing is being executed on generators. And you can see the most important part again, because this is the clue of asynchronous programming. We execute things from the first job. And once they are done, because we wait for something, we execute the side job here. Okay, so the second job is being executed. That's the clue of asynchronous programming, and that's the clue that we do not block the operating system level thread. Next, when we are done with sleeping, what happens next is we return to the first task. So we carry on with executing the first job. So we can see that, hey, it works as expected. And it is implemented on yield return. And actually, if you Google things, you can figure out on the internet that there were people who were implementing async programming this way before async was supported by the C# directly. And you can actually do it. Like you can implement your own coroutine transformations in whatever manner you wish, just by using yield return. It's like very nice, and you don't need to play with all these switch methods, etc., etc. And you can at the same time implement the asynchronous programming this way. Okay, but now we will actually come to something different. We will move on to asynchronous programming with fibers. Okay, so to reiterate the drawbacks of the previous approach, we do have function callers. And function callers, they expect us to return a specific type from a method. We need to return task. What we are going to do with fibers is we will have on the C# level not exactly the same, but super similar bookkeeping code. So we will have collections to run continuations, etc. We will have the jobs which are executed under the hood, etc. And we will have all the skeleton logic for iterating through the queue and executing things. We'll get to that in a sec. But the thing is, when we do the task code, what happens is we do not have any async nor await. We just indicate the method as run internal, right? It's void method. The same goes for run internal nested. It's void method. There is not async task or whatever else. And we get the task here, and we can call out the task the method magic wait. Okay, that's the idea. Imagine that you have a regular task and you call a method .wait on the task, which blocks the executing thread and waits for the task to finish synchronously. The whole idea behind magic wait is we do not block the thread, but we still wait for the task to finish. So this is truly the magic wait, which we would like to do here. And when we get this thingy here, you can actually see that, hey, these things were executed as always. So there was one task being executed. Then when we called magic wait on the task, a side job was interleaved. And then we can actually carry on 2 seconds later. After the task, the sleeping finishes, we can carry on with the second, return to the first job and finish it. So this is how we can implement these things. Now let's see how they work under the hood. So the first thing we need to do is we need to have some stub code which does the fibers for us. So first thing is we do have helper, which I wrapped as a C++ CLI code, which goes to the operating system and calls the WinAPI methods I mentioned on the slides. So in the convert method, we do have some C++ code. Let me just scroll down. We do have this fiber helper, which gives us the convert method, which basically converts current thread to fiber, okay? And then we have method create, which creates the fiber, and then we have method switch, which switches to fiber and does the cooperative scheduling. So what happens now is, first I convert the current thread to fiber, and this fiber gets identifier of 0. So they are 0-based, we number the fibers. Then I add a new job and new fiber with identifier 1, which calls the run internal method. And second, I add the side job, which will be executed on the fiber with number 2. Okay, so initially, after we convert, we are on fiber 0 because that's the main fiber of our thread. Okay, so what I do next is when I get the job to execute, what I do is I call switch. So I call the cooperative scheduling method to basically put different user mode level thread on top of the operating system level thread I'm executing on currently, okay? So this switch goes to this thingy here and calls switch to fiber. And this switch to fiber is basically a .NET method which executes the action. Okay, and the action by default, which we provide, is the fiber start method. And this fiber start method is a bit of C++ code, which gets the .NET and which ultimately executes the fiber async method in our C# code base. So we go to C# code base and we go to, fiber async type, method called start fiber. So we go to start fiber, we get the job which we would like to execute, and we just call it. So because this all jobs is basically a collection of lambdas, and we put in this collection an run internal method, this method is being extracted in this line from the collection and then executed. And then we start executing run internal method. This is how we get here. And now we are on fiber number 1 because we did switch fiber to different one to execute this thingy. Then we call run internal nested, and the most important part is how do we do the magic wait thingy? And when we go to magic wait, what happens is we take the current fiber, we remove it from fibers which can execute because we are waiting for the task delay to finish. We schedule the continuation on the task. Again, this could be done with threads, with semaphores, whatever you wish, or EAP, whatever patterns. And when it's done, we restore the fiber to the queue that, hey, it's ready to be executed. And before finishing, we just switch the fiber to the fiber number 0. So we switch to the main fiber of this operating system level thread, right? Fiber 0 is the fiber where we start. Fiber 1 is the run internal, and fiber 2 is the side job. So because we switch back to the fiber 0, we effectively come back to this line because here we switch to fiber number 1. So we come back here and we carry on with executing this loop. And because there is another job to be executed, ultimately we'll switch to fiber number 2, okay? And once the continuation is done, the job will be re-added to the queue and we will get the job from this queue and we'll switch to fiber number 1 again. So this is how it goes. This is how it works with fibers. And you can see that this magic wait looks pretty nice, okay? This is what we always dreamed of. We wanted to have these tasks. We wanted to have asynchronous programming, but we just wanted to call wait on the task. We didn't want to put async here, await there, async here, await there, and pollute all the code base. We just wanted to have the magic wait method. And this is how it can look like. And this is how it will probably look like in the Java world. But now, this is not the end. This is not the last thing which we can do. We can actually carry on with these implementations, and let me just tweak the code a bit because we will be playing around. What we are going to do now is we would like to deal with other things which we indicated as issues or as drawbacks of the coroutines. What we would like to do is we would like to fix the way we return the type or fix the way we control the asynchronous execution, right? So we want to handle this service locator pattern, and we would like to handle this statically bound promise factories. So now we implement a monad-like monadish solution. So again, the bookkeeping code. However, the idea now is instead of running things like the regular way, we will a bit run them in the so-called like kind of functional way, and then we'll return to the regular C# code. But bear with me. So what we are doing is we want to have a monad-like type. So we have type which supports a method which gets the value from the type, runs operation on top of it, and then wraps the value in the type again. And we would like to control it this way. So again, we have this delay, we return delays, and we have the map function just like with monads, with flat maps, etc. But the important thing for us is we do have this execution environment, which we carry around. And this execution environment, it has two properties. The first property is the builder for synchronous operations. The other property is the builder for asynchronous operations, okay? So now what the builder does is it supports a single method which returns a monad of type T. And there are actually two different implementations of this builder. One of them is called ID builder, like identity builder, which just returns the identity. So it's like a box which holds the value, nothing else. It does not add logic like asynchronous programming, does it add optionality, doesn't add looping, anything like this, okay? It just holds the value. And async builder is basically a builder which uses the async monad. Now the async monad, which we have here, the map method of this async monad is it runs the things asynchronously because it gets the code, it removes it and allows this lambda to be executed asynchronously. On the other hand, the identity monad is just waits for the thing to be executed. So now see what we have. Apart from all the other things which we do have here with the delay, with the data, with the code which we have here, etc. The important thing is we do have the side job being executed, being interleaved. Okay, but notice what we can do now. We can control our environment because what we do is we initialize the async builder as the builder using asynchronous code. But if we initialize it to use identity builder and we now recompile the code and run it again, what we will get is whenever we want to run an asynchronous operation with async builder, we'll be actually using an identity builder under the hood. And identity builder under the hood, what it does is it waits for the operation to be executed. So once the code starts and once we see the results, you can actually see that this time the side job was not interleaved. This time the side job waited patiently until the first task finishes. So we can now control how the synchronous and asynchronous things are being executed just like that, just by changing this builder without changing the code under the hood, right? We do not need to step into methods with task or whatever else. We just change the builder around, and this is what we can control here and there. Obviously, you could get something like this, not necessarily the same way, but you could get something similar just by implementing your custom synchronization contexts. But that would not be the same because in synchronization context, you still deal with all the thread pools under the hood. And unless you hack .NET down to a very single detail, you cannot get this nice synchronous execution just like that on the thread you are executing. So this is what we can see. We can now control the thingy just by changing one line of code. But we can do one more thing, and this will be the last demo for the day. And the last demo for the day will use something similar to higher kinded types joined or merged with monads. So what we are going to do is we start where we have the same thing we had before, like the bookkeeping code, but this time, instead of having all these monadic-like structures with map and flat map, we just write a regular C# code, but each method which needs to execute in our execution environment, it has the generic type parameter T. where this T is the builder, etc. So what we do now is when we call delay, we pass the T, and this T can be controlled here at the very top level. So you can see that now I am calling my run internal nested with type of async builder, and you can see that it didn't work because probably Visual Studio didn't compile something. So hopefully it works after we do recompile these things. But what we would expect to see here is that the side job is being interleaved in the middle. Okay, so let's wait for it. Let's give it another try. Oh, sorry, I know what we didn't change, and that's why it's not working. Because apart from changing this line, I also need to tweak the C++ code because I am hard coding some things, just to make them simpler. Okay, so let's recompile these things again, and we will see if we do get the side job interleaved in the middle. So you can see that here we just call delay, and delay is implemented in the regular way as it was before, only this time instead of getting these builders from the execution environment, we just create the builder, and then we create the timer to do all these things, and then we continue with the timeout and with the context handling these things around. So let's see what is going on around in this code, and you can see that again, the first task was being executed, the side job was interleaved, and after 2 seconds of waiting, after 2 seconds of waiting, we carry on with the first thing, with the first task, as it was in the regular async and await world, okay? So it seems to be working. But notice what we can do now. Instead of calling run internal nested with async builder, what we can do is we can run internal nested with identity builder. And this time we are not changing any type of, any returned type from the method. We do not change task to something else. We do not change the execution environment. What we do is we just change the generic type parameter. And the advantage of this approach is, first, this could be implemented by the compiler easily because your compiler could interject or introduce these synchronous types, etc. And you can see when we switched from async to identity builder, the first task finishes successfully and waits here in the middle for 2 seconds, and only after the side job is being executed. So we can see that it works. We can not only control how it's being executed from the very top, but also we can get the advantage of compiler optimizations. Because, hey, if this is a type which is well known during compilation time, and this is what is happening here, then the compiler can introduce all the necessary optimizations to cut down on memory allocation and other things. So you do not need to now step in and change your task type to value task to decrease the memory usage. All you do is you change the builder to some structure, and the .NET compiler knows how to optimize these things and how to cut down on the memory allocation. Not to mention that you do have asynchronous code without polluting your code base with async and await, and not to mention that, hey, this thing actually works as expected. So that would be it when it comes to demos. And just to summarize what we did, Coroutines, they do not necessarily integrate with platform that well. As I mentioned, there is another talk where I explain all these things, but the important part to understand is that these coroutines, they increase the memory allocation, they do a lot of bookkeeping code, which may not be pretty well when it comes to using inside constructors, because you cannot await inside the constructor, or inside void methods, because you cannot await inside void methods easily. Global state is not necessarily flexible. We would like to control things without using any global properties. We would like to control them on a case-by-case basis. This is how we would like to run them. Green threads can simplify things, can make your code cleaner, but not necessarily faster depending on the use case. So it's not that I'm saying that green threads are always better or whatever else, nothing like this. But generally, it's good to understand all the primitives you have under the hood. And last warning, whenever you do asynchronous programming, know your synchronization context, because, hey, it's important to understand which things are being executed under the hood. And with all that being said, it's time to answer some questions. So if you do have questions, I'm happy to take them. Okay, I do see questions. So we run fiber demo using 0, 1, 2. If we want to run several tests at one moment, we can each time use 0, 1, 2, or we need to somehow keep it unique. This is a question how we are actually implementing this. Well, I just hard coded a couple things, right? If this was a production implementation, you would probably have some ID generation. You would not hard code 0, 1, 2. You would have some nice code doing that for you. Yeah, so the implementation here, do not consider it being production ready. It works, but it's not something you would like to use in production because it's just hard coding things, and we do not want to hard code things. And question 2, it's not clear how to chain continuation for new way to run async execution. So how do you chain continuation? You cannot do continue, like you could do continue with on the task the same way you do with regular task type. Yes. However, here I just focus on the scenario where you basically call a method, get the task, and just awaits it. This is the most popular scenario when it comes to async and await, right? If you would like to support different things like scheduling continuations on the tasks, doing task when any, doing task when all, etc., I do not support that in this source code. This can be supported, yes, but it would just increase the in the complexity of this demo. And well, this demo is pretty complex anyway, or the source code is pretty complex anyway, so I didn't want to make it harder. Another question: is there a limitation for fibers quantity? I do believe so, something like 30,000 or 200,000, depending on the whether it's 32-bit or 64-bit, something like this. You are just limited by your memory. So consider it the same way as there is a limit for your threads in your application, right? You do not think there is a hard limit of X, but you do know that if you exhaust memory, then you won't create any other threads. The same goes with fibers. There is not a hard limit, but your resources just limit that. Okay, are there any other questions I could answer? Are there synchronization primitives for fibers? This is a very good question. As far as I know, there are no synchronization primitives directly supported on the operating system level. Same goes for async and await, right? So it's not necessarily like a different drawback. There are libraries providing things like that. For async, there are also libraries. For instance, take a look at Async X library, which supports the synchronization primitives. But generally, there are not. And also, when it comes to fibers, .NET at some point tried to play with fibers, tried to support them inside the CLR directly, and they decided not to do so because of lack of operating system level support. That was one of the reasons. So this is a very good question, and the answer is no. The same as with async, right? With async, you do not have synchronization primitives either. Any other questions? Okay, there are two more questions. First, performance. Does it really noticeably better for fibers and IO waiting? How much? So is it better for fibers? I don't know. I haven't measured that. That was not the goal. This could be probably slower when it comes to IO because, hey, you need to go to your operating system level to do the IO. But I don't think it would be a noticeable difference because, well, for IO, you just need to wait anyway, right? But I haven't measured that. This could be faster, could be slower, cannot comment. I would expect this could be tiny slower. I wouldn't be much concerned about that. Second question, not the question, just a comment. Code maintainability, it looks well too senior level. I agree. This code you probably would need to hide in some library, would need to encapsulate in some Nugget package. So it's well tested, it's used and implemented by some people who actually understand how it works under the hood. And then in your source code, you just use the magic wait method or whatever else you need, right? Just like with any library. But the whole point of this talk was to show you how it can be done. Know that it only can be done, right? But how to implement that. And there is also a comment, would prefer any way to make it back as neat as async await are. Well, if you do have .wait method on a task, and you do have this method, then, well, this .wait method could just do what I'm doing here with fibers under the hood. You wouldn't be concerned much. And this is what is how it's going to look like in JVM world, right? You will have a thread which you don't care about whether it's a user thread or operating system level thread. You just code .wait on it and it works. Another question is fibers do not work in .NET 5, right? That's actually a bit misleading question. The answer is, well, you cannot, the fibers do not work in .NET framework either, right? Because they are not directly exposed. That's why I need to use C++ CLI or whatever interop thingy to go directly to the Win API level. However, the C++ CLI or the interop library would work in .NET 5. At least as far as I'm aware, this would work in .NET 5. But I haven't tested it, to be honest. But I don't see a reason why it would not work. It's just a matter of calling some Win API methods, so it should work. And one more comment, thank you for the presentation. Thank you as well. Glad you liked it. Are there any questions I could answer?
Yeah, guys, if you don't want to type your question, push raise hand and I will switch on your microphone.
Okay. I guess that is all when it comes to questions. If you do have...
Yeah, seems like... No, we have.
One more. Is it possible to run such a code on Linux? This code I presented to you, nope, because it runs on the fibers, which are Windows thingy. You could implement this code, but you would need to get some other threading library on Linux. For instance, you need to go with, I don't know how they are called, these libraries, but there is a green thread. There are at least 2 different green threads libraries for Linux, which are well standardized in POSIX or whatever. So yeah, the concept would work on Linux as well. You would just need to go with different interrupts. And another question, if some code is running in Fiber, would it not be a problem to call a dispatcher? Well, if you do call a dispatcher and then you get a message, but because dispatcher under the hood calls some message and puts it to the queue, then this is the thing which you would need to control as well, because if you get a message on your thread, then depending on which fiber you are on, you may get some unexpected results. But conceptually, this could be implemented and this should work as well. Only the .NET dispatcher is, since it's not aware of your fiber logic, you would need to make sure that whenever dispatcher steps in and your message is being processed, then on each thread which you use with dispatcher, you basically handle fibers the proper way. But yeah, technically this could be implemented and this should work. Are there any other questions? Okay, I do not see them.
Yeah, we have.
Oh, there is one.
Yeah, just a second.
Hello, thank you for your very interesting and hacking presentation. I have a question about this Fiber Zero that was a dispatcher in implementation before Monad 1. Isn't it another static thing that we are trying to avoid? I mean, that fiber that in turn checks the message queue and executes all other real work fibers. Thank you.
Okay, thank you for this question. So the question is this Fiber Zero observing the queue actually a static thing or kind of service locator, which we would like to avoid as well? Probably you could think of it this way, but the answer is, like, we cannot get rid of it. We need to have some piece of logic which does observe the queue. This is how it's implemented. With async anyway, right? Whenever you do have a continuation running on a thread pool, then basically each thread from a thread pool is observing 2 queues. You have local queue and you do have global queue. So your thread needs to observe the queue anyway. Whether we do it in Fiber Zero, whether we hard code 0 or have some nice method for getting this number, not to mention that 0 was just for ease of implementation. It's like an implementation detail, but you need to have this logic, observing the queue. At least I don't see an easy way to get rid of this observing the queue completely. And if there was a way, it would probably rely on some low-level primitive, like operating system level primitive, which in turn would do the same. So while it is some sort of static code, I agree, it's something we need to have anyway, and it doesn't break things for us. Because the problem with static, which we are trying to address in Async and Await, is not necessarily that that the static code is there, but the thing that this static code is exposed to our business logic and can be modified. Just like with synchronization context in Async and Await, anything can step in and modify the synchronization context for us. This is something which would not happen here, right? Because it's not the code which we are calling or service locator which we are calling. It's just a skeleton under the hood, just like a message queue on your WinForms UI thread, which takes the message that the button was clicked and dispatches it later on. So I wouldn't consider it being that big of a problem. Could be. It's like a tiny implementation, so I haven't explored all the drawbacks of it, but I wouldn't expect this to pose a significant issue.
Thank you. And another question: what if we have several, let's name it, main fibers, and is there a necessity to switch between them? I mean, like you have several thread pools, and here the same way that you could, instead of continuing on main fiber, you could switch back not to zero, but another zero.
Yeah, okay. So the question is, can we have multiple dispatchers, multiple fibers named 0 or numbered 0? This is just an implementation detail. Like, imagine that you have a library which gives you this async skeleton, and it just uses the fiber 0. It could use multiple fibers, like 0 or another 0, yet another 0, and differentiate between them. It's up to the library how it implements these thingies. So it's not a problem. We could have it. It would probably, it would work exactly the same way. That's how you implement the library, how you would like it to be working. The tricky part would be, okay, what if I have async implemented just like here I shown you, and I want to call some another async library which also uses fibers to do the work? How does it work then? And this is actually the situation when these things could break, because depending on how you create these fibers, they in theory could run into some problems. But conceptually, it's exactly the same as you have with the regular multi-threading programming, right? You execute code on your some thread, and then you call some library which does create a different thread, right? Do you think of it, is it a problem? It could be. You could have deadlocks, you could have synchronization issues, right? But generally we know it can work, right? And we use these things all the time, and they do work, okay? So the same thing could be done with fibers. You would just need to, think, that's the whole point of these fibers. You should not consider them being different from the regular operating system level threads. Just think of fiber being a fancy name for a thread. That's all. That's how we should think about that. And in that case, everything should work the same. So if we have proper libraries, well-tested, well-designed libraries, all these things should work the same way, should not pose any problems.
Yeah, thank you. It was my concern, and you have totally answered it.
Cool, cool. Are there any questions? Okay, I don't see any more questions. So a couple references for you. Obviously, I haven't mentioned that, but you probably figured it out. This QR code points to us to slides. Slides are also on my blog, so you can access them on the internet easily. Couple references for you if you'd like to read about the .NET platform. Couple books for you. I highly recommend taking a look at the Old New Thing blog by Raymond Chen. This actually covers plenty of fancy hacky thingies, just like I showed you. Also, a couple links pointing to my blog about Async and Await, about the Async Wandering series, where I basically cover all my free talks and all these things. And also a couple more references for you if you'd like to read about async in general, about outside on my blog, but still on the internet. So feel free to take a look at that. And being all of that said, it's time to call it a day. My name is Adam Furmanek, I'd like to thank you for coming here, for attending this talk. Hope you like it, hope you enjoyed it. Feel free to drop me a line or email, Twitter with more questions if you had them. And thank you.